Okay, continuing on with stochastic matrices and crossing over to Markov chains. Again, a matrix is stochastic if it has the characteristics of being square and where all the entries inside are non-negative and where the sum of the probabilities for each column will end up at 1. And crossing over to where we have working with Markov chains. Okay, now for the variable terms we have, in the case of the variable p, okay, they have the numbers and characters in the subscript, and those are what are referred to as transitional probabilities or transition probabilities. And for what I have labeled, okay, for the column headings, you're looking at kind of referencing like the state you're transferring from. And for the row sections that we have designated like S1, S2, all the way down to S of n, this is the state that is being transitioned to. And we're going to put up a bit of a case, kind of like an everyday example, and which might pose as a little bit of a surprise at the end. I know I was a little bit surprised by the result. And where Markov chains are concerned, okay, now we had this rule of thumb that the nth state of a Markov chain for which P is the matrix of transition probabilities and you have uppercase X naught is the initial state matrix is going to be where we have X of n is equal to P to the n times X naught. Okay, so again, X naught is the initial state matrix. And just kind of make sense of what the variables are going to represent. And we have, as a case, all right, we have in a population sample of 10,000 restaurants, you have 5,500 that serve Coke, and you have for the rest, you have 4,500 that serve Pepsi. And in the sample, you have a setting where serving Coke and serving Pepsi are mutually exclusive. So none of the 10,000 restaurants will be serving both beverages. And we have, on average, okay, at least with the trends, okay, there's a 20% chance that the restaurants serving Coke will switch to Pepsi. And from the other end of the spectrum, there is a 10% chance that the restaurants serving Pepsi will switch over to Coke. And we have with these developments, okay, we have posed a couple of questions. Okay, the first, how many restaurants will be serving each beverage in 1 year? And then we have subsequent to this, okay, also a temporal question, how many restaurants will be serving those beverages in 3 years? And this is where the use of the Markov chain is going to come into play. And so just looking at what we have, and I have like a couple of ellipses, or I should say ovals, okay, consisting of Coke and Pepsi, and just looking at the numbers. Okay, so you had 20%, this is in reference to switching from Coke to Pepsi, and the 10% you have going from Pepsi to Coke, and then we have just with the clockwise patterns here, you have 80%, that's the likelihood that the restaurant serving Coke will stay with Coke, and for the 90%, you have like those serving Pepsi will stay with Pepsi. And we have kind of summarizing or setting up in terms of a probability matrix. Okay, so you had the matrix of transition probabilities. Okay, so you have like for Coke to Pepsi. Okay, so you have your column headings with Coke and Pepsi, row headings also with Coke to Pepsi, and making sense of the numbers. Okay, so you have like Coke, the probability of staying with Coke again is like 80%, and then going from Coke to Pepsi, okay, this is a 20% probability, and from what we have going from Pepsi to Coke, again, there's a 10% chance. And just staying with Pepsi, from Pepsi to Pepsi, or just staying with Pepsi, in other words, it's reflexive, 90% chance. And again, this matrix is stochastic. Okay, it's a square matrix, and the sum of the probabilities in each column, okay, we have to be 1. Okay, so sticking with Coke, for restaurants already serving Coke, 80% chance. Switching over to Pepsi, have 20%. And again, from looking at it through the lens of restaurant serving Pepsi, again, you have 10% chance going from Pepsi to Coke, 90% chance of sticking with Pepsi. And for what we have from the start now, again, 5,500 out of the 10,000 restaurants serve Coke, and we have initially 4,500 out of the 10,000 restaurants serving Pepsi. Okay, so just looking at it in terms of percentages and just setting up what we have for the probabilities. Okay, so we have 55% serve Coke, 45% serve Pepsi, and the initial state matrix, again, converting from percent to a non-percent decimal. Okay, so you have the initial state matrix. Okay, you have 0.55 for Coke, 0.45 for Pepsi. Okay, if you notice, okay, we have for the transition probability, it had the reference to Coke at the top and the reference to Pepsi on the bottom, and I want to maintain that particular symmetry or pattern, okay, for the initial state matrix. Say 0.55 for Coke, 0.45 for Pepsi. And okay, so we got the P and the X naught, and in 1 year, okay, using the Markov chain, okay, so again, we have X of n is equal to P to the n times the initial state matrix. Okay, so with n at 1, so x1 you have just P times X naught. And again, we have with the transition probability matrix, again, we have the same 2 by 2. You have 0.80, 0.20, 0.10, 0.90, and we have times the initial state matrix, again, which we have at 0.55, 0.45, and again, just multiplying the matrices together. So you have 0.55 times the first column of the transition probability matrix elements, and then you have plus 0.45 times the second column elements of the transition probability matrix, and just looking at adding the corresponding parts, and we have for what we have for the outcome. Okay, so you have x01, that's the state after 1 year. So you have 0.485 in reference to Coke and 0.515 in reference to Pepsi. And okay, so after 1 year, okay, still with the same sample size of 10,000 restaurants, okay, there is more drastic change than even what I was expecting. And you're going to have Coke with 4,850 restaurants serving that beverage, and Pepsi will have 5,150 out of the 10,000 restaurants serving that beverage. Okay, and I thought that the tide would turn, but I did not think that the change would be so drastic. Now, in the case of what we have in 3 years, and again, just going back to the Markov chain, you have x of n is equal to P to the n times the initial state matrix, and here we have n is equal to 3. And again, you have the transition probability matrix, same 2 by 2 matrix, and again the initial state matrix, again you have 0.55, 0.45, and if I'm looking at the cube of the transition probability matrix, now we have for the square of what we have for the transition probability matrix, okay, and in this one, okay, so we've got in this layout, okay, so you have squaring out, you're just carrying out the same pattern and methodology. Okay, so we're going to have for the square, first column is going to have 0.66, 0.34, second column we have 0.17, 0.83, and then just taking the cube of the transition probability matrix. Okay, so you can see we have P times P squared, and in this particular case, right, just kind of continuing on with the same methodology, but just different numbers in the mix. And we have for the cube of the transition probability matrix, and so we have for the first column we have 0.562 and 0.438, and for the second column we have 0.219 and 0.781, and using that and multiplying by the initial state matrix, and we have after 3 years, okay, so you have the state after 3 years, you have P to the third times X naught, and so for what we have in this outcome, taking the numbers here from the initial state matrix, so you have the top number times the first column of the cube of the transition probability matrix, and you have plus the bottom number times the second column of the cube of the transition probability matrix, and gathering the numbers, and we come out to about 0.4077 and 0.5923, and actually came out to like 0.40765 and 0.59235. And I just chose to round up with the top number, though I could have done it with the bottom number. And just with the option of going with rounding up for the top number. Okay, you're going to have for Coke, okay, you'll end up with about 4,077 restaurants serving it after 3 years. And as for Pepsi, the numbers keep going up. So where in 3 years you have, out of that pool of 10,000 restaurants, you'll have 5,923 of them serving, once again, Pepsi.